afternoon. Good afternoon and all. So again, we are talking about the analysis of indeterminate structures. That Carney's method. So the steps are involved here again. So we have to determine the fixed end moments, compute the rotational factors by using relative stiffness. And here in the figure 1 again, so what we have discussed about the K values for the different conditions, support conditions for fixed. What will be the K value? Continuous, what is the K value? So roller, fixed, hinge, simple, support, like that. So these are the steps involved again. So now here we have to analyze a continuous beam by Carney's method. Here the support B sinks by 0.25 centimeter or 2.5 mm. I is equal to 3500 centimeter to the power 4 and E will be 2 into 10 to the power of 5 Newton per mm square. Sinking at support problem. So here only the sinking at B only. Sinking at B. So it will be affected. So it will be affected BA span as well as BC span. So there is no any effect to the CD here. So now as per the procedure, so we have to calculate the fixed end moments, but here there will be a sinking, so the fixed end moments plus the sinking moments will be added. Fixed end moment plus sinking moment should be added for the final fixed end moment. So here I is equal to 3500 centimeter to the power 2. Sorry, it's 4. It's 4. So E is equal to 10 to the power of 5. Then check whether all the dimensions are in mm or meter. So check the input value. So you have to check. So is it all the values are in mm or meter? So we have to convert all the values in meters because the length will be in 3 meter and the load will be kilonewton per meter. So all the dimensions on the units are kilonewton and meter. So convert this. Sink or level difference at support B is effect only for member AB, BA, BC and CB, not for CD and DC. So here there will be a figure here in that. So how to calculate the delta value for the different members. For the member AB and BA, delta is 0 plus 2.5. See, so whatever may be the sinking, you have to add these two values. 0 plus 2.5, that will be affected both the member AB and BA. 0 plus what is the direction here? Direction is very important. The clockwise direction, that's why plus 2.5. So 2.5 mm will be the delta value. Now come to here. These directions, standard directions are very important. Minus 2.5 plus 0, minus 2.5 plus 0. So it will be minus 2.5. So that will for member BC and CB. So here there is no value, here there is no sink at C. So it will be 0 and both the values are 0. So delta will be 0. So here determine the fixed end moments. So earlier we know that. So 6EI delta L square minus 6EI delta L square will be added. So these are the sinking moments. How to calculate the sinking moment for delta values if the delta value will be. So 41.67 again 6EI delta by L square 18.33. Here the delta is minus 2.5. So minus it will get plus. So 6EI delta by L square, 6EI delta by L square. So here there is no any sinking values. So we should not consider 6EI delta by L square for this. If some of the problems C will be given, so then you have to add these two. So I will talk in the next session. So in the next step, so we have to calculate the rotational factor. BA, BC, C, B, C, D. So K value will be there and summation of K 0.8333. So if you don't want, you don't calculate this directly. You can calculate the rotational factor minus half into K by summation of K. So here this problem, why I am considering this problem only for the sinking. So if the sinking will be given, so what should do? So this procedure, you have to draw this figure in the exam or in the practice. So you have to draw this figure. This figure is very important. By using this figure, you will get very easy values as a deltas. The rotational contributions again. So these values are the iteration values. So here simple calculation. The rotational factor into 19.58 plus far end value. So initially it will be 0. So 19.58 multiplied by 2, you will get this value. Divided by 0.2 multiplied by 0.3, you will get this value. Now come to the here joint C. For joint C, so M dash BC will be the far end value. This plus of this multiplied by rotational factor, you will get this value. This plus of this multiplied by 0.2, you will get this value. So first iteration will be clear. The next second iteration, so you have to add the MFB plus far end moment into distribution rotational factor. So you will get 3.443. So same value multiplied by 3, so you will get 5.165. The next 5.165 plus of this multiplied by 0.3, you will get this value as per the procedure. So what we have followed for the iterations, first iteration, second iteration for the joint B as well as joint C. So here 0.2 multiplied by the MFB far end will be 0, far end will be 0 in the next case. So the far end is 5.874, so you will get these values. So in the second iteration, so 2.363, so this will be the far end value. So you will consider for this, and 0.2, first time 0.2 and 0.3, you will get these two values. For the joint C again to calculate. The next, similarly, third iteration, fourth iteration and fifth iteration. So you have to check with the fourth iteration, fifth iteration. So here some value, some correction is there. So here, so we are considering, so fourth iteration and fifth iteration. So that fifth iteration will be the final contributional moments. Fifth iteration will be the final contributional moments. Then next final net moments. So same procedure, MAB is equal to MFAB plus 2M dash AB minus M dash B. So only M dash B is there, 3.397. So MFAB is minus 41.67. So you will get minus 45.07 in the BA. So MFBA plus 2M dash BA plus M dash AB. M dash AB will be 0. So it was 3.397. 18.33 is fixed end moment of BA. The same procedure will be adopted. So you will get the final moments. Draw the bending moment diagram. So initially you have to take 45.07, 06, then 11.533 and 40.96 and 35.77. Just add all the lines, all the points. So like this. And this will be bending moment diagram. If UDL, it will be parabolic. If it is a point load, it will be like this. If it is a point load again, so if UDL, you can this. If UDL, it will be WL square by 8. For point load, WL by 4. So UDL, WL square by 8. So next calculation of shear force, it will be the same what we have calculated earlier. So first you have to take the summation of moment at B equal to 0. So here this point. Next you have to check RAB multiplied by up to B 3 minus, see the direction, clockwise direction. Next 40 into 3 into 3 by 2 plus MAB 2 moments, MAB and MBA equal to 0. So you will get RAB value Then next RFY. So all the vertical forces should be equal to 0. So here RAB plus RBA is equal to 120, 40 into 3, 120. Already you will get 71.18. So 120 minus 71.18, you will get 48.82 RBA. Next come to the span BC. Summation of moment at B equal to 0. Next RCB into 2, 100 into 1, MCB and MBC equal to 0, you will get RCB value. Then next, so again RCB value, so RBC plus RCB you will get 100, RBC is 35.29, RBC plus RBA you will get RB value, RBC plus RBA you will get RB value. The next summation of moment at D equal to 0, so you have to calculate the D as the same procedure. Then this will be the shear force diagram. So take a line. If it is a UDL, so take the line here. So total load minus of 71.17, so you will get this value. The total load UDL minus of 71.17, you will get 48.83. RB minus of 48.83, you will get 35.29. RB minus of 48.83, you will get 35.29. If it is a point load, take the straight line and come down. So the total load minus of 35.29, you will get this difference. So that is 64.71. Take the 64.71 like this. What is the RC value? RC minus of 64.71, you will get 76.73. The total load, UDL load, minus of 76.73, you will get 73.27. So how the shear force diagram will be drawn. Thank you. Thank you. Again, the multiple choice questions will be there. So you have to solve the multiple choice questions, MCQs. And along with, there will be a PDF and a Word file will be there. So you can go through this. Thank you. Thank you one and all.